Welcome to the ChemDoctor, and this is the third video in the series that started with the aldol addition and went on to the second video, which was the aldol condensation. And in this video I'm going to describe the Claison condensation. Now, all three of these organic reactions involve what's called a condensation, and what the viewer needs to understand about condensation is we're talking about the fusing of two molecules. So in the case of the aldol addition and condensation, we were combining two aldehydes to make one larger molecule with the elimination of the small molecule water. So the aldol condensation involved what we called a dehydration because the small molecule that was eliminated was the water molecule. In terms of the Claison condensation, we're going to be combining two esters that are going to be fused by a carbon-carbon bond. The Claison condensation has in common with the aldol condensation the fact that we're going to generate an enolate anion in the first step, and that basically makes a particular carbon in the molecule a carbanion or a nucleophile that then is combined with another electrophilic carbon that is part of the carbonyl functional group to fuse the two molecules together. And then in this case, the Claison condensation, the small molecule that's going to be eliminated in the final step is going to be ethanol instead of a water molecule. So the Claison condensation is very similar to an aldol condensation. The major difference is that we're utilizing the combination of esters, and the elimination product is going to be a molecule of ethanol in this case. So I've laid out the reaction above here, and I've color-coded the carbon in the ester because that is going to make it easier for the viewer to follow through the mechanism here. And there are going to be two steps. In the first step, we're going to be utilizing the ethoxy anion, which is going to be in the solvent ethanol. All right, and then in the second step there's going to be an acid wash, and that's what allows us to basically neutralize the ethoxide elimination product into ethanol. All right, so let's go ahead and get started. And I've prepared our mechanism down here. So we're going to take one of the molecules of the ester. I've color-coded the carbon. I'm going to try to do that all the way through the mechanism so we can keep track of which molecule is which a little bit easier. We have our nucleophile coming in, which is the ethoxide molecule. All right, so let me label this. It's going to be nucleophile. All right, and the nucleophile, again, remember that this carbon here is our alpha carbon, and because of the electronegative nature of the carbonyl oxygen, which is shown here, and then this is an ester, so we also have an electronegative oxygen on this side. So the bottom line is that the hydrogens that we have in the alpha position to the carbonyl are electrophilic. All of these hydrogens have partial positive charges on them, and so I'll put a partial positive charge here, and then we can show the nucleophilic attack like this. And these electrons here are going to, at least initially, I'm going to put them back on this carbon. And we have essentially formed the enolate ion. So let me go ahead and redraw the compound now, showing the enolate anion. All right, and remember, this is a resonance stabilized intermediate. So here's the enolate, but also it's a carbanion because we have a pair of electrons that's residing on this carbon. And I'm going to put some brackets here because this structure is in a resonance relationship with this one. All right, so here's your enolate. And I'm going to leave a gap here because we're going to do our mechanism right out of this box. And remember, this is, I'll label it to help the viewer remember this. This is our enolate ion. And this is the thing that is most similar to the aldol condensation. All right, now I'm going to change this carbon here because I promised to keep it color-coded as we go through this. All right, so now let's move on in the mechanism. So what I'm going to do now is I'm going to draw the other ester molecule here. I'm going to flip it around because it just makes it easier for me to do the mechanism. And remember, this is an ester. Whoops. All right, so this carbon here is electrophilic. All right, it has a partial positive charge on it. And this is a common thread that we've been talking about now through the aldol addition and condensation, and now with the Claison. All right, so the oxygen, the sp2 hybridized oxygen is negative, the carbonyl carbon is positive, and we can have the pair of electrons here on the alpha carbon make a nucleophilic attack on the electrophilic carbon that is part of this ester. All right, and this set of electrons is going to come up like that. All right, now I want to go ahead and redraw our intermediate here so it's clear cut what's going on. All right, so I'm going to move this guy down here now. And I want to keep color coding this carbon. Here's our alpha carbon that was the carbanion. All right, and notice that we still have two alpha hydrogens in play here. And that's going to be important to us in a minute. And then here's the result of this initial nucleophilic attack. All right, and this is the part that makes this the ester, what was the ester, right? And then this is the CH3 group. So going back into the mechanism, I want to point something out that's important that your professor may ask you about, or may be an important thing that you have to emphasize. There are two proton transfer reactions in this reaction, and the first proton transfer event was right here. Remember that you can basically boil down much of organic chemistry into proton transfer events on one level or another. And this is a beautiful example of that. The initial nucleophile here is a very strong base that is somewhat sterically hindered, right? Because you've got this ethyl group that's attached to it, all right? And it is basically abstracting the hydrogen that is here. Now, in a minute, we're going to be coming on to the second proton transfer event, and that's going to be important to talk about because these two proton transfer events are central to this mechanism. Everything that we've done up to this point right here, the viewer needs to realize in terms of equilibrium, everything here is favoring the reactants. It's only in this next step where we undergo the acid wash that utilizes Le Chatelier's principle to literally drag this reaction to the right. So now what's going to happen is we're going to have what's called our nucleophilic elimination. And this starts with this set of electrons coming back in to form the carbonyl double bond. And this moiety right here, or functional group, is eliminated like this. So we're going to end up with an intermediate And I'm going to continue to color code this thing. I'm switching to blue. So we keep track of the original carbonyl carbon. All right, and we have a carbonyl oxygen back in this position. All right, and we kicked out this molecule, so let me draw him back in here. So we have the ethoxide anion again that's still in the reaction. All right, and this guy is now, remember, we have these, this carbon here is an alpha carbon. It's now literally sitting between two carbonyl functional groups. So both of these hydrogens are acidic. So let me go ahead and put the partial positive charges on these guys. All right, and the ethoxide anion comes in and takes this hydrogen. And we form an anion on this carbon. So let me go ahead and get that drawn here. There's the electrons. And I want to, like, I promised I would do this. Let me just continue to indicate this carbon here. All right, so you can follow it all the way through. And now this is where we get our acid wash. All right, and this is the thing, this is an important step to this because it is the thing that's going to drag equilibrium to the right. Because up until this point, equilibrium favors very, very heavily the reactants of this reaction. So it's at this point where we basically, the acidity that's being used here is to basically protonate this anion. All right, and so it's another proton transfer reaction. And we get our final product here. Which is going to look like this. Okay, now, so the take home of the Claison condensation, again, what it has in common with the aldol is that it's a condensation, so we're basically fusing two molecules together. We're making a new carbon-carbon bond. What differentiates the Claison from the aldol is that we're going to eliminate ethanol instead of eliminating the water molecule. Like the aldol condensation, the thermodynamics, the equilibrium, and the delta G favor the formation of the reactants. It's this second step here that's super important because this basically utilizes Le Chatelier's principle to shift the reaction to the right, and basically in a way of thinking, you're fooling equilibrium because this product is being systematically removed from the reaction. So as far as equilibrium is concerned, it doesn't see a product at the end of the line, so the reaction keeps shifting to the right. All right, now with that, I'm going to go ahead and close the video. I'd like to thank the viewer for watching. You can find more videos at www.chemdoctor.org, and I hope this was helpful. All right, and we'll see you on the next go around.